The second derivative test. Suppose that the second derivatives of this function we're working with f are continuous on a disk, with center AB. And suppose that the partial of x is equal to the partial of y, which equals 0. In other words, this is saying that simply the AB is a critical value. That's all this is actually saying. Okay, so what I'm going to do is I'm going to let D equal, notation-wise, D of AB, which is actually equal to the second partial of x times the second partial of y minus the partial of xy squared. And I'm going to use this D as a test to determine whether or not I have local mins or maxes in 3 space. Now, I'm not going to go through the derivation of this. If you're interested in it, then I'll give you some information on it, but I'm not going to actually go through the derivation of this here. So this is how we use this result. If D is positive and the second partial with respect to x is also positive, then f of AB, the function at that critical point, is a local min. If D is positive and the second partial is negative, then f of AB is a local max. If D is negative, then f of AB is not a local min or max. It's a saddle point. And last, if D is 0, then the test is actually simply inconclusive. Okay, now, in terms of this guy right here that we're using, it may be easier to try to remember this in terms of a determinant. So this is D, this is the determinant of the second partial of x, and then y then x, and y. So if I take the determinant of this, what I end up with is f xx, f yy minus f yx, f xy. But remember, these functions have to be continuous to begin with. If we don't have continuity, then we're not even talking about this. So by Clairaut's theorem, these two are equal. Fxy is actually equal to fyx. So what that gives me then is fxx fyy minus fyx squared. So let's go ahead and go back to our example, and let's apply the second derivative test to see if we can figure out that previous example I was messing with, try to figure out if we have local mins or maxes. Now, just very quickly here, f of xy is x e to negative 2x squared minus 2y squared. And we said the partial with respect to x was, let's see, I get right down here somewhere. There it is. E to negative 2x squared minus 2y squared times 1 minus 4x squared. And we said this was 0 for, actually, this is write the critical points up here. See, critical points was negative 1/2, 0, and 1/2, 0. So I need the second partial, so fxx. That's going to be, see, negative 4x e to the negative 2x squared minus 2y squared times 1 plus 4x. Oops, that should be negative 1 minus 4x squared. 1 minus 4x squared plus e to negative 2x squared minus 2y squared times, what is that, negative 8x, which I would write as, see, factor this guy out, and I'll have e to the negative 2x squared minus 2y squared times, and see what I have, negative 12x minus, don't forget that one, I'm going to have 16x cubed. Okay, I also need to take a look again at my partial with respect to y. And that partial was negative 4xy e to negative 2x squared minus 2y squared. So my second partial with respect to y is going to be negative 4x e to negative 2x squared minus 2y squared plus, see, I'm going to have a negative 4xy times negative 4y e to negative 2x squared minus 2y squared, which obviously I'm not going to leave like that. Let's do a little factoring here. I'm going to have e to the negative 2x squared minus 2y squared times, let's see, what's all left in here. Let's see, when I collect everything, I'm going to end up with 16xy minus 4x. So here's my second partial with respect to y. And the last piece that I need is I need the partial with respect to x and then y. Well, see, the partial with respect to x and then y is actually, where is it? Here we go. I just need to take this, because this is my partial with respect to x, and just take this derivative respect to y. And what I'm going to end up with is simply this negative 4y out in front of all of this. So this is going to be negative 4y e to negative 2x squared minus 2y squared times 1 minus 4x squared. Okay, now I need to put all this together, this piece, and what I need is fxx times fyy minus fxy squared, and I need to, let's just call this d again, and I need to evaluate this at each of the critical points. So when I take that first critical point, that is going to consist of negative 1/2, 0. What I'm going to deal with here is the second with respect to x at negative 1/2, 0, which is the e to the, well, actually, I don't need any of that stuff because this is always going to be positive. It doesn't matter what I put in there. Really, all that matters is this last piece that's multiplied by. And that's going to be, see, negative 12 times negative 1/2 plus 16 over negative 2 cubed, which equals e to the, well, something, don't really care. Like I said, that's always going to be positive. That's going to be 6 minus 2, which is 4 multiplied by whatever this is. So it's greater than 0. So I have something greater than 0 there. Fyy at negative 1/2, 0 is going to again be e to that whatever it is. Doesn't matter. It's always positive. times, it's going to be negative, where am I here? Negative 4. Let's try that again. It's going to be negative 4 times a negative 1/2, which is just going to be 2 times whatever that is, but that's positive. So both the partials second partial with respect to x and y, both of those are going to be positive. And then I need fxy at negative 1/2, 0. And that is going to be equal to 0 because that's what we use to find the critical points to begin with. So what I'm going to have is this piece right here is definitely going to be positive. And actually, I said a moment ago that it really didn't matter what this piece was. I probably shouldn't have said that. It does not in this case, as it turned out here, because it's going to be positive and this was 0. If this was non-zero, then this value could be very critical. It could be extremely critical because I'm subtracting this partial of x and then y, the value squared. I'm subtracting 0, so this did not play a role at all. But it could. So we got to be careful of that. So for this particular piece, I have d is going to be greater than 0, and fxx is greater than 0. Therefore, I have a local min at negative 1/2, 0. Now I need to repeat this whole process, and I need to find fxx of 1/2, 0. And that's going to end up being, well, when I evaluate this exponential function at 1/2, 0, I'm going to end up with e to negative 1/2 times, this is going to be negative 6 plus 2, which is obviously going to be negative 4 over e to the 1/2. And then fyy at 1/2, 0. I'm going to substitute all those values. I'm going to get, again, e to negative 1/2 times negative 4 over 2, which is going to give me a negative 2 over e to the 1/2. So again, I'm going to end up with d greater than 0 because I multiply those two together because that's what constitutes d. And fxy is again going to be 0 because that was a critical point, and that component ended up in there. So I have d greater than 0, and the second partial with respect to x less than 0. Therefore, what I have is a local max at 1/2, 0. So now if I actually find f of negative 1/2, 0 and f of 1/2, 0, that will actually give me the coordinates of those mins and maxes. I'm not going to do that here. You may want to just for the heck of it, but obviously that's how I'd find exactly what the values are of those mins and maxes.